Hey, how's it going? Getting things set up here. All right. Today we have plans to get our AI that can track clicks, well, predict the next user click, and we're going to train it with more synthetic data. We've been training it with real input data. Hey, Neva, how's it going? Merry Christmas. Good to see you. Saw your message there in Discord. Thank you. It was neat. I was neat to see a little Merry Holiday Christmas message there. SAQ 3000, how's it going? Merry Christmas. Well, Merry Christmas. We're going to continue our user click tracking with the AI. I think we can, I don't know. I'm not fully sure. I know we have to create some sort of recognizable pattern that the AI could learn from. Obviously, if it's random clicks, we like see here on the screen right here. If we do this right here and we make it fully random, how is the AI gonna learn? You don't celebrate, but thanks. Oh, well, thank you. Thank you for sending the message. The plan is we're gonna make sure, I'm not sure how to, it can't be fully random. It cannot be entirely random because if it is, how could it possibly ever learn? It'll just be noise, right? So then if you need to be able to track what a human's gonna, so we need to think this part through. That's what I'm saying. We got to think this part through. Improved model for better accuracy. We can make some changes on how we're training the model. So, and then we could also add some hotspots or heat, or sort of like a heat map effect. We could add that as well. So that's the plan for today. That's the plan. We can get right into it. Focus in good. What is Steven meant? Oh, wait, what? What do you mean? Are you like maybe what was good throughout the year? Hey, Addy Legendary, how's it going? Merry Christmas. Take existing data, slice it. Existing data is user input. It's really the clicks. That's all we have. We don't have any other existing data at this point. Although I suppose we could grab some from maybe some Kaggle. I don't know if Kaggle has click data. We could probably do that though. We could probably get some Kaggle click data. Steve, I got that part. SAQ 2000, I got that part. Like add a bit of noise, slicing and rotation to real data. Oh, got it. So then we have some fuzz data, and then we have real data. That could work. Hey, Kevin McAllister. Hey, you caught the live. Merry Christmas. Merry Christmas, Kevin McAllister. You made it. Good job. Great to have you here. That's what I meant. That's what I meant. Yeah, Merry Christmas. We're going to continue our click AI clicking. Steven is in holiday mood. Yeah, I know I am. I've got my sweater on. I don't know if you could tell what kind of sweater it is. You might be able to recognize the character. I don't know or not. Maybe. Video game character. Famous video game character. You probably. I won't say anything. Merry Christmas to you too. Merry Christmas. Thank you. Hello and bye, Neva, SAQ, and Kevin. Eddie Legendary. We're all here, everyone. We're all here. All right. Let's see here. What else can we get here? Let's see here. Mario. Oh, come on. No. You're doing that on purpose. I mean, it kind of looks, if you zoom in, I guess it kind of does look like Mario. There. It's not, though. It's he's got a sword and a shield. So Mario doesn't have the, it's kind of hard to see. Maybe there's a slingshot. I can't tell. What is this slingshot? It's a shield. It's a shield. Steven is emotionally vulnerable. You made my day happy. Merry X person takes advantage of this vulnerability. I'm sorry. Sorry about Zelda. Yeah, well, it is. Yeah, it is Zelda. So you're on the right track. It is from that game, right? Legend of Zelda. You got it. You figured it out. Kevin McAllister, you figured it out. It is the main character from Legend of Zelda. All right. So what I want to do is improve the model. Let's see if we can improve the model for accuracy. I think what is our current optimizer? We are doing Atom W. That seemed like it should be fine. We could change the loss because this is just an average, right? So we could probably change the loss to find something that's more pattern oriented. What are the different loss functions in Pytorch? Let's see if we can find this. Pytorch loss functions. What do we got here? Is there a bunch? Pytorch loss functions. The ultimate guide. What varieties do we have? What loss functions are available to us? All right. We're going to figure this out. I was rewatching your own movies. Oh yeah, you were. Home Alone for the holiday season. Forgot how much those fun those were. Nice, got it. Those are like perfect for holiday movies. They're perfect holiday movies. The what is this? I've never seen that loss function. What is that loss function? Have you L1 loss? Have you ever seen an L1 loss? I've never used that. That's kind of interesting. Never know. Yeah, Home Alone was one. Nice. Oh, hey, there's others. I didn't think about that. I didn't think that there might be others beyond Home Alone. Is there? What is L1 loss? Also called, the mean absolute error. Oh, not the mean squared error, but the mean absolute error. All right, so it doesn't go negative. It won't go negative. Yeah, also the computer screen is less than half the screen. Oh, right. Oops. I I had it in full screen mode. There we go. All right. Now you can see what's going on a little bit better. You can see a little bit better now. See the screen. So L1 loss, I've never tried this. This would be neat to try. The sum of the absolute differences between the actual values and predicted values. That seems fine, I suppose, right? Although I don't think we want that because it could go negative, right? It could go negative. So we'd rather have the mean error. Good morning, Leaf. How's it going, Leaf? Leaf on Blossoms. Leaf on Blossoms. Merry Christmas. We are doing some AI today. Let's see here. We are reading through the different loss functions. L1 loss, MAE loss, output. Okay, looks good. Oh, MAE loss looks good. Backward. And that would compute the gradients, and then we optimize. Separate steps, you guys. Hello. Halio? Wait, Merry Christmas. Hello. Happy to have you here. Because absolute. You got it. No, it can't go negative, right? It can't go negative. It cannot because it's absolute. Because it is the mean absolute error, not the mean squared error. See, this is the one I'm used to, mean squared error. That's the one I use. Also called L2 loss. Woo, we're learning new things today, aren't we, you guys? L1 is good for classifieds and support vector machines. The more we know, SVMs support vector machines, you guys. All right, Pytorch MSE. This the one is the always outputs positive results. But wait, hold on. wait. Well, I guess because it's squared, right? So since it's squared, so if it's a negative, then it will positive type as well, right? Because two negatives make a positive when they're multiplied. So it makes sense that they're always positive in that case too. All right. And the perfect value is 0.0. Was there a perfect value? Yeah. No. All right, what do we got? Is there a perfect value for L1? All right, perfect value. Nope. They're all 0. I mean, of course they should all be 0, right? Because of the loss, we're all here together. How's it going, Sane? Sane, how's it going? Merry Christmas. Hi, how's it going? All right, so punish the model for making big mistakes and just encourages small mistakes. Oh, does it? Interesting. Mean squared error. Okay, so yes, L1, 0 for L1. All right, good to know. The problem with F1 is that lower loss doesn't necessarily mean the answer is moving in the right direction. More we know. We're learning here. Okay, let's keep going. Let's see what else we got. So MSC, that's what I'm used to. What is this one? Log likelihood loss. So I've never done this one before. Applied only to models with softmax functions as an output activation layer. What do you know? Oh, I could have used this. I could have used this previously. Oh, I could have used this. All right, we're figuring things out. All right, so negative log likelihood. LL loss. LLL. 3 L's. Destructive and constructive inference are cool. Are they? This is neat. We're getting into it here. He has 2 streams, 1 portrait and 1 landscape. I do, yeah. We're on 2 different streams. We got 2 different streams going because it was requested. You guys said, hey, where's the horizontal stream? So I'm like, all right, we'll get that one going too. All right, so that's neat. Negative log likelihood. I like that. It's kind of hard to say. It almost feels holiday-ish, right? Almost a little bit holiday-ish here. Negative log likelihood. Might want to do e to the negative x to the power of 2 if you want to model a Gaussian. Ooh, a nice Gaussian curve. So you get those real, like, those real nice wavy blue, like real nice. Yeah, that's a neat. Never Gaussian. The more we know. So that's Gaussian, is it? Or is it? Do you say Gaussian? I'm not sure. I'm not sure. Simplicity is awesome and would. Yeah, I like simplicity. I'm way down with simplicity. I like simplicity. Time to make Plum loss function. We could make our own loss function. We absolutely could. We could make something innovative here. With some dropout, it should actually be the same as Bayesian model. The more we know. The more we know. All right. How to decide on the architecture. It's all based on what you're trying to optimize for, what the inputs are, what are the outputs. Mostly what you're trying to optimize for, right? I mean, that's what machine learning is. It's all about optimizing towards it. Gaussian with an OU, like deep U. I'm not as familiar. Now we're getting out there. Now we're Blum loss function, right? We could do it. We could do a Blum loss function with the code waiting for chat to score the answers. We could. I like that. Maybe we do. Maybe we could. I mean, why not? We could. It might not be very good. At least we could make something that would work, though. We could absolutely make something that work. Hey, Ashford, how's it going? Merry Christmas. Merry Christmas. Good to have you here. Ashford, hey, everyone. Ashford is here. All right, multi-class classification problems for negative log likelihood loss. All right. Softmax is the final output. M loss, M. Okay. M input. Where's input? Okay, here. Oh, got it. Okay. And target. Got it. Nice. Okay. Cross entropy function, right? Okay, so is that like classification? Is it good for classification? Computes the difference between two probability distributions, providing a set of occurrences for random variables. It is used to work out a score that summarizes an average difference between the predicted values and the actual values to enhance the accuracy of the model. You should try to maintain minimum score, the cross entropy score between 0 and 1. A perfect score is 0. Okay. When do we want to use it? Binary cross. Oh, so binary BCE. All right. I know that one. Binary cross. So it's 1 or 0 between the two, right? Between 1 or 0. Think you probably just L2 because your model log likelihood of a Gaussian. Can't see why you would want to do anything else. I mean, that's a good point. I mean, we're just trying to figure it out. Right now we're using MSE, right? So that's the one I'm used to. So we're using MSE, as you can see. MSE right here on the screen. How much machine learning AI would you say you are good at? And how did you go about learning, implementing papers, E2E? Yeah, so I started this before Pytorch came out, and TensorFlow was just kind of coming out, like it was new. So this was about 15 years ago now, and that's when I was really getting into it. Yeah, just MSE is the GOAT. Yeah, that's the one. That's the one I use all the time. I use MSE, and so I've always implemented it myself by hand from scratch before the frameworks came out. So now what I'm trying to do is see what all the possible things that I missed over the years, and trying to learn the frameworks themselves directly. That's what I want. You can also use distance, absolute distance, or something else weird. I haven't heard of that one, absolute distance, which is probably just the subtraction, straight up subtraction. Is that absolute distance? Is that what you mean? With that, instead of going native, so you absolute value of the distance. We could do that as well. Okay, so we're just kind of looking through the different loss functions here. Where we got here. Okay. Cross entropy. I know binary cross entropy, and then Pytorch versus TensorFlow. Okay. They are able to achieve the same goal on the outcome. They have the same same framework capability. You can do transformers, you could do convolutional neural networks, you could do whatever. You can achieve your goal. Now, TensorFlow with Keras, easier. Less code. Everything is pretty built in. You don't have to write as much code. It's great. Pytorch, more flexible, gives you easier access, I would say, to integrating. From my background, where I come with from scratch, I could bring my own algorithms along with it. However, when you do that, you break the graph. You need to implement your Pytorch using all the native Pytorch functions. Hey, Robbie, thank you for subscribing. Merry Christmas. This channel is all about AI, machine learning, software engineering, and that's what we do. We write code. We turn off the AIs and we write code from scratch using our hands. Like use case would be L1, I think. Not sure. Need to get my figure out. Also, yeah. So what I like to do is the brute force method. I like to try all of them and see which one works. Kevin, you missed a few streams. Predictions of the user clicks. Where? Oh, okay. Yeah. So just over the past few days. So they're just the past 3 streams, I think. Whenever you need to show examples or mess with models, you take Pytorch model because you can look at the guts. Yeah. So Pytorch, I've gone more down the Pytorch route. I would say TensorFlow with Keras is easier to use and get started with. Not using AI to make AIs, right? Exactly. We turn the AIs off, the AIs, and we're making our own AIs. All right. So I'd like to try. So this page keeps scrolling. Hinge embedding loss. What are all these for? So we've got a margin ranking loss. Wow. Triple margin loss. Okay, so that's just a increase. Let's see here. What else we got? Callback labor divergence. Where are we going with all this? Tells the output you the proximity of 2 probability distributions. Okay. If the predicted probability distribution is very far from the true probability distribution, it'll lead to a big loss. All right. And then you train in your heavier weight on your initial training. So that's kind of neat. KL divergence behaves just like cross entropy loss, with the key difference in how they handle predicted and actual probability. While cross entropy punishes the model according to the confidence of the predictions, that means KL divergence does not. Okay. Well, there's no. We're not even halfway through. We're not even halfway through all these. This is ridiculous. No, I mean, where are we predicting clicks of users like in game? Oh, so I'll show you real quick. Okay, so let's see. Python main. Okay, here. So we've got ourselves a click. Here we go. So you can see here, the yellow is the AI, where the AI thinks the user is going to click next. And let's see here. What I want to do is, here's what I want. I want to remove the learning rate decay. I want to remove the learning rate decay because I'm seeing that so I can click, right? So as you can see, it reduces over time. I want to remove the learning rate decay and make it a little bit more heavy up front. All those are for classification though. Yeah. And we're not doing classification at this point. We're doing, coordinate prediction. And so we have an encoder and decoder that is able to handle it. Oh, it's learning in real time. Yeah, learning in real time. Exactly. Like reinforcement learning. KL is cross entropy minus some of the constants. Like it's both a whole bunch of letters that you put on the screen. I never. Very weird distant function because it isn't symmetrical. For us, in our case, it's definitely not symmetrical, right? Mostly it's random. So that's some of the things we got to all right, so I want to look this up really quick. WAtom on Pytorch and see if we can change the learning rate decay. How to change learning rate decay for Pytorch opt_atom. All right, how do we do that? LR scheduler. All right, so we need a new LR scheduler. Decays the learning rate of each parameter. So in our optimizer, is that where it's done in the optimizer? All right, parameters, weight decay. Is that it right here? So is this, how does that work? Oh, let's see here. All right, weight decay. We're learning about it. We're figuring things out. Oh, it's not a transformer? Oh, it's just standard feed-forward neural network with deep, full, what do you call it? Dense? Full full matrices. There's nothing crazy going on there. We might change up the model. We might add some dropout or something, or maybe some regularization, a couple other things. We'll figure it out. Different outfit today. Yeah, it's Merry Christmas. Carmu, welcome on in. Merry Christmas. Good to see you. Let's see. Getting through some of the chat messages here. Let's see. Oh, wait, Neva. You might actually want to try KL. Make the model won't overfit on new data, like LLMs usually do, so we could add it to the raw loss. Good idea. What happens if you combine multiple loss functions? I mean, you could average them out, right? You could do one loss function and do another loss function and then average them. You could, although the gradients wouldn't, when you're doing the gradient compute, right? I could do it manually, but if I did that here, so wait, back here. So yeah, this would, I wonder if you could like, do it more than once, right? Would this stack? Can you do would it update the existing gradients? Like, how would it stack? I'm kind of curious. So there's a bunch of different things here. Merry Christmas to you, Mr. Blum. Thank you, Carmo. Thank you so much. Merry Christmas. So it's like a refuelizer. You minimize the KL to the old version. Like KL is usually used as a loss equals predictions plus KL prediction old model. Okay, we'll try to remember. We'll try to remember. We'll see if we can remember that. All right, here we go. Where else do we want? All right, so I wanted to change the rate of decay. Scheduler exponential learning rate. Optimizer scheduler. Okay, initialize the scheduler. Is there? Let's see here. Optimizer. All right, let's go to dark mode. Thank you. Okay. Optimizer. Okay, you have to give it an iterable containing the parameters. Right. Here, the iterable with the parameters. All right, good. Learning rate and momentum. Okay. So momentum is its own thing, but that's also with just SGD. So SGD might be different. Sum of all the losses, then backward that. Yeah, never, right? That's exactly what I want. That's like, that would be neat. I would like, I know how to do that manually. How do you do it in Pytorch? Bro, you look like Sunyo? Who's Sunyo? Wait, who's Sunyo? Sunyo. Who's that? Well, that's obviously a company. Oh, wait, Sunyo? What is this? Dr. Sunyo? Wait, maybe. I don't know. I'm sure. That might not be the right one. Manually is fine in Pytorch. Loss isn't special. It's just a function. That's a good point. Okay. Parameters. Another parameters. Named parameters. Base. Classifier. Momentum. Now, can I do momentum in any other? Or is it only for SGD? Weight decay. Okay, so what is weight decay? I want to learn this. Let's learn rate decay. What do they call this? Weight decay. In case they differ. Copy set of parameters. Nope. That's not it. Okay. In this manner, biased terms are isolated from non-biased terms, and the weight decay of 0 is specifically for. All right. We're figuring stuff out. We're looking at ways to deal with Pytorch. Essentially, we're trying to deal with it. Yes, the cartoon from Doraemon. Oh yeah, Doraemon. There was a Doraemon themed Harvest Moon that was released. I got it. I downloaded it and I played it. It was really neat. It was unexpected. Like Story of Seasons or Harvest Moon, if you're familiar with the franchise. There was a Doraemon version of that. It was neat. I enjoyed it. It was a lot of fun. Atom has momentum as well. Actually, SGD with momentum is a subset of Atom. Oh, okay, got it. That makes a lot of sense, Neva. Thank you. All right, Doraemon. Yep. I remember that. I do. Like there is a paper making that case called On the Convergence of Atom, which basically says they're all the same and same convergent. Okay, good to know. Okay, so weight decay. I want to know what weight decay is. Is there... Just see. Deep learning basics. All right, so let's do this. Pytorch, weight decay. What is it? Weight decay is a regularization technique by adding small penalty, usually to the L2 norm of the weights, all the weights in the model, to the loss function, right? The loss function. Weight decay parameter times L2 norm of the weights. Okay. That might not be what I'm looking for. It might be, though. It might be. Hey, Sagar, how's it going? Merry Christmas. Welcome on in. It won't converge as the same model. Won't converge with Atom or SGD. Okay. All right. Long time? Yeah, long time. What do we do? What are we coding? So we've coded here with the help of quantified quantum, created a click predictor. Well, quantified quantum wrote the clicking animations that you see here on screen, and then I wrote the AI that tracks where it thinks the user is going to click next. And I'm trying to like generally click in each of these coordinates, right? So always do. Is it predicting where I'm going to click next? It's getting close, right? It's like it says, oh, it thinks it's going to go there. It thinks it's going to go there. So if I keep clicking in these corners, it should start learning where I'm going to click next, right? Because I'm doing like this corner click, and it kind of is working, right? Click, click. Oh, it's getting closer and closer. Isn't that neat? It's learning. It's learning pretty good. It's learning pretty well. That's pretty neat. So it technically we already are good, right? Technically already good. We're just trying to make it a little bit better, is what we're trying to do. Make it a little bit better. And so what I would like to do is what I'm doing right now, make the computer click in this pattern and see if we can get it to learn this pattern here. And it is. You can see it's learning to go on either side of the screen, right? So it is. And it's finding the average between where I'm clicking each side of the screen. Isn't that neat? So it is. It's learning. That's really neat. Oh, it's just so neat. It's just so neat. I like it. Weight decay works like Banyan Prior. Good. I just realized how much of AI and I nerd you are. Yeah, I know you've known all this stuff. It's all the math from years ago. You've got a good memory. You've got a good memory, Neva. Fantastic memory. Isn't this neat? Yeah. So it's getting pretty close. I want to improve it. So I want it to get like spot on. I think we could do that. So I want to create a series of clicks so that way the AI can make it happen. Hey, what's up, buddy? Baggish. Good to see you. Are you Christian? Or Bayesian is like Bayes' law. All right. The more we know, we're learning out things. Let's see here. Okay, so it thinks there. Click, click. Clicking. So what I'd like to do is let's see if we can do those clicks for us automatically. Let's see if we can implement the clicking. Let's see if we can got that too. And then once we have the data being generated for us automatically, then we can start playing with all the loss functions and things like that. And like exactly what Neva's describing in stream right now. Bayesian is like all the different things. Gotta automate the mouse clicks. Yeah, there we go. So you can do like 1,000 steps all at once. That's what we're gonna do. Yeah, we're gonna automate the mouse clicks. Yeah. Baggish. Yeah, I do. You were here previously. Yeah. Remember me? You got it. Let's see. All right. So let's see if we can. Let me click a few things here. 1 second. And then we're gonna create a for loop, and we're going to loop over and get all of the clicks automatically for us. Which kind of goes against like, hey, this is going to be like full on reinforcement learning in a natural, real environment where the AI is learning on the go. It's fine though. It's fine. We need to generate some synthetic data, I think, to get it up to speed first. Okay. So event marker and Python marker. All right. So I want to add some points here. We need to add some points to the marker. Event hook. Oh, look at that. Oh, neat. Oh, that's kind of neat. What do you know? Drawable event hook pass. Okay. So there's a nice little event button lift, print, and push. Okay. So otherwise, there's a self.push. So I probably can just run def push. marker dot push, self point, and it's a list. And the point needs to be a certain thing. So it needs to be like this, right? Position. Okay, so I basically just need to do this, and then the event dot position, I need to figure out what that is. Print and position. Okay. So what is this? When we figure out what this is, then we can do this automatically ourselves. So that is already being printed, and it looks like this right here. Okay, so this is what it looks like. Thank you for the likes, you guys. Saw a little floaty heart icon show up there. You could record your mouse clicks. Oh yeah, that's a good idea. I could even just record them myself, and then have the turbulence so it's kind of random. That's a good idea, Kevin. That's a good idea, Kevin. Why did you need synthetic data? It won't just a smaller model fix this? I don't, just from a performance, what do you call it? I want to iterate more quickly. And me clicking a few times on the screen to get just a very small number of samples, it takes time, and I'd rather have something that we could launch. It trains on some data, and then I see its progress immediately. We close it, reopen it, close it, reopen it, and do sort of thing like that. So it's just part of the model tuning that we're getting. That's why. That's the whole reason. That's the whole reason. Question: are you inferencing an already trained model? Oh, this is a from scratch model. So we're not doing post training or fine tuning. We're training from scratch. So just record like 20 clicks. Yeah, we could. There we go. We could do 20 clicks. We could record 20 clicks, and then just run from there. You're right. Okay. So since you got it, thanks. Yeah, thank you. Good question. Merry Christmas. So let me see here. I want to. Let's see if we can do record 20 clicks and then replay them. We'll do that. We'll record 20 clicks and then replay them. Let me see here. Where should we do that? I suppose. Because, all right. All right. So we've got it here. Marker, event. Okay. So event hook. And then it says it's a click. So this is a button. All right. So here we could, to do save click, in a array or a list, and then we want to, after 20 clicks or so, and then actually better idea, right here, save clicks. Here we go, to do, because that's where it exits. So we save the clicks here, and then we record the clicks, we load the clicks, and then we remove the save, because we'll just have a bunch of sample data. Okay, so that's the idea. Okay, so we could probably do it with the JSON. We can do JSON serialization. So let's see here. Event hook. Let's capture the clicks first. Self dot clicks equals an empty array. Oh, wait. Whoa. Oh, whoa. Look at this syntax right here. A list of lists. This is just a regular list. Clicks. This will be like XY coordinates. So we should be fine. We should be fine on that. This is pretty neat. I didn't think. Is that possible? AI list points. That's pretty neat. Maybe just save over the old save every time, so it's fine to open it again. That's a good point. We could absolutely do that. Like potentially on a Control S. Yes. So let's see. Let's capture the clicks first. Let's capture the clicks. So here's the clicks, and then this is the data type. Okay, so colon list. We could just do that, right? That's probably fine. Although I suppose we could do a list of lists, because that's basically what it is. It's a list of lists. Okay, so there's the clicks. Let me say historical clicks or something like that. Previous clicks. There we go. There, and then we need to push onto that. So where is this? Here. Okay. So here. Dot push. Well, can we say dot append? Is dot push a function? When did they add dot push? Python's always been append. Python. Let's see. A equals A dot push. Zoo, weird. B list of lists equals empty array. B dot push. Yeah. Oh, right. I remember now. Okay. Push is, let's see, we do append. So push is different. Push is a predefined function. Here. That's why that's doing it. Okay. I got it. Local like this is tiny. Yeah, it's gonna be very tiny. It's like a pre-LLM in machine learning. We're talking like 5+ orders of magnitude less. It's gonna be way less. What hardware are we using for training? CPU. We could use GPU. We don't need to. See, this very tiny model. We're just doing click tracking. Yeah, I was thinking push is in JavaScript. Yeah, I was like, what's going on here, right? And so I'm like seeing all these errors. I'm like, see, I told ya. And then I realized, oh, right, I forgot. Quantified Quantum wrote this code ahead and wrote the method push. Here, this is the method right here. And that's being used here. For us, though, we're going to be using append. And we will be doing the event position. However, I need to see what that is. Before, because it needs to be serializable. It looks like it's a tuple, which should be fine. It should automatically convert into, well, here. Let's see if we can do 0, comma. We'll do this. We'll do it like this. Like that and like that. So there we go. Okay. So that should work. All right, so let's print this. Print previous clicks. Okay. Perfect. Okay. Let's try running that now. Okay. Let's see here. I need a Vim tutorial from Steven. Yeah, Vim is great, isn't it? Because you could jump around and do no need for the mouse. It's phenomenal. I love it. I think you're going to argue CPU is actually optimal here because we don't need to move data. Yeah, you're right. You're right, Neva. You're 100% right. Because the rate is going to be like this. Okay, so let me see here. I'm going to see all my clicks. Yep, that's exactly the kind of data format I'm looking for. Perfect. Okay, so we got the input data. Okay, so here, we can close that. Previous clicks. And then we also need to render. We'll render the previous clicks. Although... We'll just use this. We'll use this pattern to render it later. Okay, that sounds good. That's fine to me. Perfectly fine to me. I think we're good. You started move from Sublime to Visual Studio. Yeah, there we go. Sublime has been great. It's a wonderful text editor over the years. Now Visual Studio's kind of taken over. You're really fluid in it. You use Vim Motions. Yep. In VS Code. Yep. There you go. You could use Vim Motions in VS Code. You absolutely could. Switch from lazy Vim so you don't use AI, but find it difficult to split the tabs. Yeah, you can do all these splitting and things like that. You can split around if you need to. I do that sometimes. I do the split sometimes for if I'm trying to reference different parts of the code at the same time in the same file. Been a happy girly? Nice. That's great to hear. Oh, do you use Haskell for it? Oh, that's a question. Why are you using Haskell? That is a good question. All right. Let's put this a little bit down here. Okay, make it pretty. Okay, so I need to capture this. Where is that? I want to event hook. Okay, save the clicks. Okay, so we need to import JSON. Import JSON, and then JSON.dump. Right. So let's see. There we go. JSON.dump. I think, and we need to set it to a file. How do we do this? We need to Google this real quick. All right, save JSON file JSON.dump because it's not dump s, it's dump dump. We need to open a file. Okay, like this. Okay, so do something like that. Copy paste. Excellent. Okay, JSON.dump data, and it will be what our clicks were. Previous clicks. Here we go. Right here, looking good. Data file. Let me just do that. ILE. We don't need to indent. So maybe we can just do it like that. Okay, perfect. And then we need to load it on boot. We need to load it on boot. And then we need to add all the clicks. How do we want to do this? Maybe every frame we could replay the clicks. I think that's like a good idea. We could replay the clicks every frame. Want to try my hand at checker and dependent types. That's a good reason for Haskell. Steven just showed off his Vim skills, and I didn't tell us the key bindings. It's just the normal key bindings. It's just the normal key bindings. I don't actually remember what they are. It's just natural now. It's just keystrokes. Potentially some borrow checking. Oh, nice. That's pretty neat. That's a pretty good idea. That can be fun. Also, C is a language I work with a lot, and the grammar is such a nightmare. Ooh, gotcha. Well, C is a small keyword set. In the language, C is pretty simple. It's pretty streamlined. Okay. So all right, so we saved the data. Now we need to load the data next. So I think JSON that loads. Okay. So when let's see if we can actually get it saved first. Let's see if we can save the file first. Let's make sure it works. Click. Looks good. Okay. Close. Self.previous clicks. Oh, whoops. Okay. Where are previous clicks stored at? Marker. No, is it marker? Wait. I think it's marker. Okay. Marker equals marker. Event hook. So I think it's marker dot. Okay. Marker. Yeah. Yes. Okay, perfect.
Hope everyone has a good Christmas. Let's shake off this year and keep pushing next year too. Merry Christmas.
Okay, it's getting going here. Looks good. The point marker. Yep. Okay. That should load now. Oh, hey. Kiddo Royale. I missed your message there. You said, hello, hi, Merry Christmas. Welcome on in. All right. See, click, and then close, and it doesn't error, and we should have a nice finding data file. All right. We should call this clicks or something. I want to call it data file. Let's call it clicks. Better. RM data file. Okay. Now we did the save clicks. Now we need to do the load clicks. Let's do the load clicks. All right. So where's our marker happen at? Our marker. I wonder. We could. Where's it? Marker equals here. So we could say. See, open as read. So here we go. Okay, the clicks equals JSON.load. And then we will just say file. Perfect. Okay. There we go. So that should do it. And then I suppose that gets us, well, okay. No one can read function pointers in C either? Yeah, that is true. That is one of the hard things to deal with in C, especially when it comes to pointers for functions as well, right? Not just pointers in general. Okay, fine. Pointers to functions. Are we doing callbacks? That's one of the patterns that I've used actually on a regular basis in C. I really like referencing a function or a pointer to a function by passing a function as an argument. It's a fun pattern, and C supports it. It's amazing that C supports it, and it allows you to do a lot of fun patterns that I've used a lot. No, we're coding a C compiler. Oh, okay. Well, that's a slightly different conversation. Good to know. Okay. I want marker equal dot what was it? What was our where it was called previous clicks? Okay, will be equal to clicks. Equals clicks. There we go. Get rid of that. Indent this. Let's just put it over there. Okay. We don't even have to. We don't even need this. I think we could just do this. I'm pretty sure. All right. Now let's see if this works. Print F previous clicks. Marker previous clicks. Let's see if that works. And in case the file doesn't exist, also we need to do a read. Somalia, how's it going? Merry Christmas, you're back. Good to see you. We're getting this. We're messing with our AI that tracked and was able to learn where to click, where the user's going to click next. We were able to get it to work. We've got the AI, we've got the model. It works really well. It does what it needs to do. And now we're trying to make it a little bit easier to iterate. So we're going to capture all the user clicks. And Merry Christmas. Yeah, thank you. We're going to save the clicks and then load them in. So that way we have more data every single time. And when we train the model, this will allow us to more easily be able to manipulate the model to fit best tracking the user click. Specifically, I think we need to change the input features to show a series of click coordinates more than what we have right now, because we only have 2 coordinates as the input. And then the output predicts based on the last 2 coordinates where the next click is going to be. I think we need more. So that's what we're going to do. That's why we need to track all this. So is that how that's going to work? I don't know. I'm making this up. I forgot. So we need to do a try catch try. Let's see here. Except. Let's see. How do you do try except Python again? I always forget the except part. Can we just do it like that? Okay. That's already what I have it at. I already have it at that. Okay, perfect. Print no previous click file loaded. Excellent. Okay. Load previous clicks. Perfect. Python main. Let's see if this works. There should be no previous clicks loaded. Yep, exactly. So let's click. Let's do some clicking. Close. Reopen. All right, let's double check. Vi clicks. All right, we got our clicks here. Excellent. Then we want to run again. Oh, what about a long-term short-term? Yeah, the LSTM. That might be like the next thing, right? I mean, we could. Giving you infinite history. Like that model architecture it's old, right? Or recurrent neural network or LSTM, right? But no one uses it ever since Transformers. Yeah, I know, right? Now that we're in Transformer world, that would be another way. So we could migrate to a Transformer, see if that works better. We can do LSTM because there's a few clicks. All right. It still says no. Because maybe the file name is not matching. Clicks open. Was it called clicks? Yeah, that should be it right there. Clicks, right? Clicks.json. Read. Oh, I might be LOAD. Okay, there we go. My try except was not working right. Vi clicks. It's only be a few clicks that time. Okay. So basically, when we do this, every time we load, click, and then reload the game, it should continuously be loading more clicks into our data set. Guess LSTM, since there's little need for history here, LSTM gives us a bias towards new stuff. Okay, got it. Which we might want. You got a quick question. All right, Rish, what do you got? I have been given a task to create a consolidated source for evaluation metric. Like for regression, absolute error, MAPE, and RMSE. So a single consolidated score combine those evals. Oh yeah, you could absolutely do that. there's no reason why you wouldn't be able to. I mean, you create all those loss functions, you capture the output, and then you capture your labels, right? So you can bind all of them. There's no reason why you wouldn't. The only thing is, if you're using a framework like Pytorch, like I am, then your back propagation, I'm not sure how that part works, because you can only do a back propagation for the gradient calculations on one of the loss functions. Can you actually, let's look that up really quick. Let's do this. Pytorch combine multiple loss functions with back propagation. So for gradient calc. Let's see if we can do it. Is it possible? Combining multiple loss functions, Pytorch back propagation is achieved by summing them into a single scalar tensor and then calling backward on the combined loss. You can do it in Pytorch. You can. There's a native way to do it. This is really neat. Are you comparing models? Because then you can rank every one of the... oh, that's actually a good... Okay, so Neva asks a really good question. Are you trying to combine them, or are you trying to rank them? Because you do them independently. You can also do more than one backward. See, that's what you can do backward multiple times. So you could do... That's what I've never done before. I've never done that in Pytorch. I know how to do that myself. Like, obviously, I could do that myself. And then combine them. Yeah, that's what I want. I want to do that too. No, Steven, you can back propagate as many losses as you want. Just sum the losses. Yeah, that's what I was thinking. So I think you can just combine the losses on the output and then run a backward. I think that would work. Obviously we could do that ourselves, but let's see. Think you may need some tricks to do it. Yeah. Let's see. Let's see what the code looks like here. Simple model. Here we go. We've got 2 criterion. And then 1 optimizer. So, right. So, how do we deal with these criterion then? Loss 1, loss 2. All right. So there we got the 2 losses. And then combine the losses. How do we... Oh, then you just add them together. There we go. Neva, you nailed it. You nailed it exactly. Every word you said was perfect. It was perfect. Right here. Here's how you do it. We're looking at it right there on screen, you guys. You see that right there? That's how you combine multiple losses into one. And then you say loss underscore combined dot backward, right? If that's what the next step is going to be. Yep. Loss combined dot backward. Right there, right there. There you go. Isn't that neat? Hey, we're learning new things today, aren't we? We're learning new things. We should keep the model simple and small, so the next stream you can compute the model by hand on paper. Yeah, no. We've done that previously. We don't have to go back there. It's a lot of fun. It does take a little bit of time to do that, though. It does. It takes a little bit of time. Like given a pre-trained PKL or any other format with eval metric, and basically I have to show the user a single consolidated score, not aggregation. What's the difference? What do you mean? What's the difference? I bet you could do this more elegantly in NIM. Right, Michael? Yeah, you're always onto it. You're always on it, right? The NIM programming language. We probably could. This is great. So if you want to have multiple loss criterion, you can do that. Total loss. And then you just say it backward. You have to, the only reason this part works though is because it's Pytorch magic. Pytorch magic function. Okay. Okay. Let me see here. All right, so we're just trying to load our JSON clicks. We're not even there yet. Okay. Let's see here. By clicks looks good. All right, close. No quit, please. Thank you. Python main. Okay, let's get some clicks recorded here. Click, click, click. Okay. We'll close that. Okay, so what I really want is to see, all right, so 151. If I click once, is it going to add more clicks by clicks? So here. So the last click is 668 by 430. So if we open this and we do one click, 668 by 430, and I do one click right here, and it'll be close to 1, 13 and 14. I should be able to close that and then reopen this, and it should be 13 and 14. Yes, perfect. Okay. Now we've got ourselves a click history. So what we need to do is every frame run through that click history when we load the model, and then run that through the training. So that's what we got to do next. Okay. So now we've got all of our previous clicks. Doing some weird combination is kind of just less informative. Like me as a user, I have no idea what I'm looking at. I wouldn't know either. We're just trying to see if it's neat. It's possible, right? It's possible to do, and it's neat that you can do it. It's just neat, especially in Pytorch. It's neat that you can do it. Arraymancer? Like Arraymancy, right? Wait, is that actually a project? Are you just talking it like, is that actually a project? Wait, you check out Arraymancer. It sounds like a magic trick, right? Tensor n-dimensional array project in NIM. Oh, neato. Okay, so it's NIM machine learning library, and it uses OpenCL as a backend. Very nice. Arraymancer is a tensor project in NIM. The programming language NIM. The main focus for providing a fast ergonomic CPU CUDA OpenCL ND array library on which to build scientific computing ecosystems. There you go. What does the syntax look like? That looks pretty neat. I like that. That's pretty great right there. So you've got your features and labels. Then you've got some, what is this? Some burned vendor mode, vendor monde, row, vendor monde. Okay, echo. Oh, interest foo. Okay. Oh, to tensor. Okay, that's pretty neat. That is pretty neat. Thank you for sharing that. Thank you for sharing Arraymancer. I like that. I like that name. That's a fun name. Okay. Now that we've got that, let us train the model on those things. I also want to visualize them. I think that would be fun. Let me see here. On clicks. Let's see here. La la la. Looks good. Okay. Marker. Previous click position. I want this to be previous click position. Position is going to be a int that is equal to 0. Okay. And then we are going to, for every frame, we're going to increment the click position until we exhaust the previous clicks. So that's what we're going to do here in our main render loop. So we'll visualize them. Additionally, we want to run predictions or train the model as well on those clicks. So we want to do that as well. I suppose what we could do is manually just import them directly, although they would all show up on the screen all at the same time. So, which I think is fine. It's just not as fun. Let's see here. If Lin, and it's not called, I think it's marker. Here we go. Marker, previous clicks, greater than that. Then let's draw. Because we don't want to delete them. We just want to move a pointer, essentially. We want to move a pointer. Okay, so marker previous positions, plus equals 1, plus equals 1. Okay, then I want to, let's see, we could draw a circle here. We could draw the circle, or we could run it through the event and create our own event and then make it a click. So that way it just runs through the regular click and it does everything else that we want it to do. So I think we could do that. Do click. Event hook click. Okay. We'll do this. But we need to make a custom event. A Pygame event. Okay. How do we do that? And then how do we update the position? Or, well, you know what? There's not a lot of code here, so I suppose we could just do this. We can move this into a function. Def append. Do we want to do that? Self point list. Previous clicks. Push. All right, so that's where that pushes. I suppose, well, event.position is what I need to figure out really quick, which is a tuple. So this is a tuple. So we can convert it into a tuple and then run push, which is marker.push. So we could do that. We could do marker.push. And we don't need to reappend it here. So in fact, we should be running this and nothing else. Okay. Okay, let's do that. And it will be called marker.push. Okay. Right here. We don't need that. We need this. Okay, perfect. And then this will be, the click will be the previous clicks at the marker position, which will be this. And then we will do a tuple, and it will have click 0 and click 1, like that. That should be fine. I think that's it. I think we did it. I think we did it. I love all the AI talk that's happening in chat right now. I think it's really great. This is so neat. I see all your chats there, and it's just really fun to see and look up, and it's like you're all talking in this mathematical terms. This has got to be like the most technical. If you look at all the different YouTube lives that are happening right now with all the chat right now, this very moment, it's there's probably not hardly any. This might be one of the few that is talking at this level of math in chat right now. Isn't that neat? I think that's neat. Stephen, can you give some input further on it? I wasn't reading as much. So they want something similar for classification with accuracy, precision, recall, and F1 score. Well, F1 score is just a really simple version of your of how good it's very close to the precision and accuracy of your model. So recall will be data that is already seen, right? So that'll tell you how good the model is able to perform on data that's already seen. F1 could be a score on data that it has not seen and has seen. I can't remember, but F1 is very similar. F1 score, meaning, what is this? I forgot. Metric, classification model, accuracy, balancing, precision with how many flagged items are correct. Okay. Recall how many actual positive items are found into a single value. So, I mean, out of all the items the model predicted as positive, how many were actually positive? So this part's really easy. So you've already trained the model, and now you're just running existing data and new data over the model to see how well it's performing. That's it. That is some easy. That's like the easiest part. I know it's like the aftermath of training the model, and it's the easiest part of the whole game. It's so easy. Well, that I search for F1 score on Google, it's 100% different. Really? We've got different AIs. Literally, F1 score is just an aggregate of the other three metrics. Okay, so F1 is just an overall. It's an overall score. Yeah, that's right. Okay, so it was pretty close. Mine chose Wikipedia, and the formula in an image is the first thing. Let's see. Yeah, I don't have that. Wikipedia isn't even on the top for me. I do have some images, though. F1 score, precision over recall. There you go. Precision over recall. That's it. So these are like the easiest parts of AI, everything. It's just your measurement of how well the model's performing. It's just harmonic mean. Harmonic mean of precision and recall. There you go. There you go. We're figuring it out. We're figuring it out, you guys. We're figuring it out. Okay. So now that I've done this, is for every single frame, when we load the game, it should go all at once, right? We should see like a big click storm when we load it up. A big click storm. Let's try it. All right, so push, click, click, click. Okay, so let's find out. Let's find out if we're going to see a big click storm. Oh, it crashed. Okay, previous. Oh, well, of course. Where'd that at? All right, here we go. Marker. There we go. Okay. Fix that. Okay, now we're good. I don't know if I'll be able to show. Yep. Okay, I saw. It was really neat looking. It was neat. You couldn't see it though. You couldn't see it because it didn't show up on screen. It was very neat. It was really neat. All right, so maybe we could slow it down. We could slow it down. Is there like a current frame? Do we have a frame counter? I see FPS. It was really neat. It was pretty. It was pretty. It was really pretty. Okay, how do we show it better? We could slow it down. I suppose we could just say frame 0, and then we'll say frame mod 10 0, and we say frame. Well, what we should do is we should increment this. We should increment it here. So we'll just say, where do we want to do that? Down here at the bottom, frame plus equals 1. Okay, perfect. Okay, that way it happens. All right, there we go. See, it's pretty. It's Christmas. They're Christmas lights. Let's add some more clicks. Let's add some more clicks. Also, I think it's clicking twice. Is it doing double click right now? Chords. 1 second. I think it might be double clicking. 463, 465. Let's go over here. Let's go to 1. Let's go to very small numbers. Where's that at? Chords. Prediction. Chords. Loss. Chords. That looks weird. Something weird's happening. Yeah, see, it's going. What is this? What's printing there? What is that? What's going on? Just joined the live. Tommy Gunner, how's it going? Tommy Gunner, Merry Christmas. We're updating. We're creating an AI that does click tracking, and it will be able to track all the clicks. So let's see here. I think I've messed something up though, because I think we've got it. Well, let's see here. Previous clicks. If frame. Oh no, this should be fine. This should be fine. I think we're fine there. If frame mod 10, and then all the clicks went through, and so it should not be clicking anymore. It should not be clicking. Print. Where are we printing it? Print the position. Right. That seems fine. Number of chords. The total count. Okay. Okay. We're good. We're good. All right. No problem. No problem. We're good. We're good. Good. Okay. All right. Looks good to me. It's chill. We're both number 1 now. Wait. What does that mean? What does number 1 mean? 1 second. Let's see here. Click over there. Tell me a bit more. The user gives the ground truth plus the model. Okay. The model or any API endpoint, and we have to calculate the eval metric for either regression or classification and give a final score. That's one of the initial things that you got to decide, either regression or classification. Chat leaderboard on who chats the most. Oh, really? Where's the leaderboard? Wait, top fans. Here we go. Oh, look at that. I just saw. Here we go. There we go. I didn't notice this before. Look at that right there. The top chats, you guys. Yep, Kevin McAllister and Neva are they're on the top. They got the same score. What do you know? Somehow Kevin McAllister, you're number 1, even though you've got the same number of XP. That's amazing. Good job, Kevin McAllister. Look at that. Let's go through Eddie Legendary, and then Risha, and then SAQ 3000, Carmu, Sagar, Saint, DZ, Michaels, Bagish, Somalia, Ashford, This is neat. Look at everyone. William, Chitaru, Tommy Gunner, Sohoy. Wow, this is awesome. I had no idea. Look at all the experience there. Look at, it's amazing. I hope I made things clear. Pretty clear, pretty clear. It's basically like a classroom, isn't it? It is. It's like you can like showing all the yeah, all the class attendance. Go for expect. Okay, all right. Thank you, Neva. Thank you for helping Rishab. Thank you for helping Rishab. This is really neat. It's great to see, and it's helping me too. It's helping me too. All right, so let's do, instead of 10, I think we should do 20 so you can see it looks a little more crispy. Or we could do, what we could do is delay. So here's all the clicks. See the clicks? I'm not clicking anything now. It's all happening magically, all on its own. Isn't that neat? See, no hands, no hands. No hands, you guys, right? See, nothing up the sleeves either. Nothing up the sleeves. We're doing good now. All right, let's add a few more clicks. What I want to do is I want to, the model seems to get set in its ways really early. And I want to see if we can, see when I click, it seems to update twice. So that's why I think I might have a weird thing happening here. Did I double up on the events? Is that what I did? Let me see here. Push. No, I should not, right? Let's see, print, previous, we'll call this previous click. So I want to make sure that this is just happening once and it's not happening twice. I'm pretty sure my logic is fine. So click, previous click is previously clicking. We're looking good there. It's working its way there. All right. I want to click into it. So I don't see the previous click when I click, which is good. All right, so now we've got enough clicks where we can increase the speed of this because this is a little slow. Okay. Wait. Oh, it is previous clicking. Oh, I get it. Because I'm appending into it, right? And so it's double. It is doubling up. Okay. I thought so. Okay. So we need an extra stop. Instead of calculating the length here, we need previous click count. That's what we need. We need to do that. So we need to store it once. Here we go. Equals. Wait. Here we go. Previous click count. Let's do this. We'll do it like that. Okay. And we'll do 10 and we'll go up here. And where was our la-la-las at? Where was it at? After load, previous click count. We need it has to be afterward. It has to be here. Okay. Looks good. Okay. Good to know. Good to know. You think you have to talk with your team lead, though? They are very experienced, and I just started, so may not be sure if questioning their judgment will be a good idea. Steven, any thoughts? You don't have to question your judgment. You say, hey, you have to be honest with them. Say, hey, I'm working with you. I'm new. I'm very excited. I want to try all these things out. I want to do all the things that you're asking. And I also would like to try out a few of my ideas that I've got from industry, my other experience. There you go. And so you're doing both things at the same time. And it's great, right? It's a really good way to work with the team. So not only are you working directly with them, following their request and fulfilling their need, you're additionally seeing if you can find additional approaches, sort of like what Neva and others are describing here in stream. You'll be able to make it best of both worlds. And you've got time because the kind of things that they're describing, they're one of the easiest things. You could do this in an hour easy, less than an hour even, because they are experienced AI engineers. There we go. Steven, no, like the weirdness is they were asked to do something that makes no sense. Yeah. So actually here, Neva, in industry and in business, and when working with others in a team, most of the time, you will get requests that don't make sense, and the requester is wrong. They're actually senior. If they're senior enough, they will understand their mistake because maybe they're making a mistake. So it's good to do both. So one side is mistaken, right? This is the great part, and I deal with this every day. One side is mistaken. So either they have mistaken, right, as a senior engineer, and they've, made a request that doesn't make any sense, which often happens, or, we're mistaken on our side because maybe there's some misunderstanding on the requirements. It is okay. So what you can do is, the best approach in every scenario is do both. Do both of them. Unless it's like a very big multi-year long task or a big month-long task that could really waste a lot of time. Try to get to the right answer as soon as possible. As senior engineers, they should accept that criticism that they're wrong because they have been used to being wrong, because it happens a lot. I'm wrong a lot. As you can see here on stream, like I make 20 mistakes before I get something working. And I'm like, hey, there we go. I usually tell them when they do something weird, yeah, that's the way to do it. You got to say, hey, there might be a mistake here, and I'm going to work with you. I'm working with you, and we're going to figure this out. We're going to figure it out together. That's the way to do it. So it's like this, sort of aggressively cheerful positivity type of approach that I described. It works really in every possible case, and you want to work with them, not against them. Do not be adversarial. Be like a teammate. All right, we're going to make this work. Let's do it. Let's work it out. And then you can present your findings in both cases. You can try what they've requested, and then you could try especially in this case, because the task in the scenario it's not that big of an ask. So you can do both. It'd be pretty easy. The annoying thing is they have one endpoint, so you need one output. Oh, they've got one. Really? Okay. Maybe it would be nice to be configurable. Have an RMSE and accuracy by default, given other options, including them all the time and relevant metrics. There you go. So yeah, when you're building this, you can side by side, especially in Pytorch, it's really nice. You could do this in TensorFlow as well. Or your own custom code for sure. Create the scenario where you're tracking both approaches. You can absolutely do it. And you can train the model using the loss or the output or however you're trying to approach it at the same time, or having two separate models training simultaneously. You could do this as well. Might as well. It's pretty neat. So best of both worlds. That's the advice. There you go. Aggressively positive cheering, or aggressively cheerful positivity. It's like, yeah, let's do it. Let's make it happen. And then when you find out that they were actually wrong, then you present the materials, not like a throw it in their face type. It's like, hey, look, you were wrong. You did it wrong. What's wrong with you? I can never trust you again because you were so wrong. No, obviously that doesn't work. You can't do that. Although it would be a lot of fun. It's like, it's a lot of fun to take that approach. Instead, you say, hey, I tried your approach, and then I tried this other one, and I've got some other output that's a lot of interest. We should take a look at this output. It's pretty neat. This reminds you of 3 weeks you wasted on your boss telling you to run some code that had a git patch and didn't work when they wanted any code to run? Oh, that is rough. That's a rough scenario. That's rough. Took you a day once you knew you needed any code? Oh, tough situations. It happens all the time, every day. It happens every day. I run into it every day. All right, I hope that was fun. I hope you like that. All right, so printing previous click. Previous, okay. Position count. Okay, perfect. Excellent. And that could be 0, or it could be 1, or it could be a bunch. So now we won't get double clicks here. Hey, look at that. It's like a Christmas tree. Check out all the clicks. Isn't that neat? Now we got all the clicks going. So see, the AI, it's barely doing what I want it to do. So we do need to change the model. All right, when I click, is it going to show previous click? No, it doesn't. Okay, good. All right, perfect. Excellent. Okay. Sounds good to me. All right, looking good. We're gonna click around for a bunch more. We're gonna click around. Hey, did any of you ever work with Evidently AI? What is that? What is Evidently AI? Tell us more. Evidently AI. That sounds like a pretty good one. Okay, so something. So I want to. Let's see here. SAQ 3000. How's it going? Welcome on. Merry Christmas. Good to see you again today. All right. Visualize the model actively as a Christmas tree. Yeah. Idea. We got the idea. It kind of looks like a Christmas tree. It looks a little, some Christmas. Let's see. So we did frame 10. Let's do. I think we'll do like frame 7. Let's do frame 7. There we go. So now you can see it looks a little prettier. A little bit prettier. Oh, whoa. The AI is jumping all over the place. Look at that. All right. So as you can see in the later training phases. So maybe what we could do is we'll reduce the size of the model. We'll see if we can reduce the size of the model a little bit. Because it seems to be learning, or it's the learning decay that's a problem. Because look, it averaged out to the perfect center. We don't want it to average out to the perfect center. It's averaging out, it's converging on the center. We don't want that. Hey, Steven, Kevin, y'all. Yeah, how's it going? Good to see you. It's amazing to just search it. Wait. Oh, all right. We'll check it out. Let's check it out. Okay. It was called Evidently AI. We're gonna look. We're gonna search it up. Evidently AI. Okay. Evaluation and observability for AI systems. Hey, there you go. Instead of doing, I mean, it is a common annoying task, obviously, to have to evaluate your model every time. It's different. And the evaluation criteria is going to be different depending on what you're trying to achieve. So it's kind of neat that there is a, what is this? Oh, we have to put in money. It wants the money, doesn't it? It wants the money. Of course it wants the money. Data rows a month? That's nowhere near enough data rows. 100,000? Are you kidding me? That's nothing. Steven got a cool hairstyle? Yeah, I floofed it up. Because I have, we're gonna see family, so I figured I'll floof up the hair. Let's floof it up. Floof up the hair. Yeah. So yeah, that's also in my profile picture. The floofed up hair version. So we got a floofed up. Okay. That's neat. Evidently AI. Thank you, Rishab. Thank you. Okay, let's jump back over to our code here. To be fair, they run stuff on that data all the time, right? Oh, got it. That makes sense. Okay. So it might be like a repeat of the same 100,000 data samples. You pay for that thing being tested. Yeah, you sure do. You sure do. Got it. That makes sense. It's fair. $50. It's a good price for that much. It really is. $50 a month is not bad. Okay, go over here. Okay. Evidently, AI is an open source ML monitoring and evaluation library. Oh, nice. So you could run it on your own hardware as well. Very nice. Good to know. Okay, let's see here. Okay, so we don't need that anymore. Okay, looking good, looking good. Okay. It would be nice if I had a add marker. I want an add marker function. We don't need to do this. We don't need to. We're prematurely optimizing here. Def add self and then point xy push append AI list point list. Okay. And then we just run push. No, we don't just run push. We run push like this. Okay. Add, and then we just say point. I think. Actually, we should do it the right way because it wants it to be a tuple. Point 1. Okay, I think that's it. So now, instead of running push like we've been doing, we could just say add. Like that, I think. I think that's all we have to do. Where was push at here? Okay, so we just do marker.add. Excellent. Stephen, what you think about portals possible to make in real life? Like in maybe, right? I assume it's so, right? You could have the wormhole approach, where you're collapsing or expanding space in some way. You've got strange matter, where instead of gravity, it's the opposite of gravity, and it can tear a hole, right? So I assume it's possible, though I don't know. That's as far as I go. That's as far as I know. I wouldn't know any other possibility than that. I thought about it a lot, and that's I assume you need strange matter, which is the opposite of gravity, pushing on the fabric and in a way where it stretches it between 2 points, as far as I could tell, and it allows you to slip through instead of collapsing in, right? So you slip through instead of collapsing into a hole. You slip through out of a hole. I think that's it, right? So, similar to how a quantum drive would work, a quantum drive doesn't move through space. It uses space. It moves space itself, right? You need a quantum drive. First thing comes to my mind is having portals is licking yourself. Yeah. What? That's not the first thing at all that I was thinking. I was thinking like Star Trek is what I was thinking, like quantum drives, and an antimatter drive, antimatter power reactor. Okay. Wait, did we do that? Right, add right there. That should maybe work. I don't know. Let's see if that works. We might have an error. I might have to fix that. All right, it's doing fine. What if we click into it? Yeah, okay. Seems to be working. Seems to be working for me. See, it's learning the average. It's learning the average. Although it is jumping around a lot more. Okay, it is. Okay, I see now, yeah. See, it always goes to the center. And I want it to not be an average. Yeah, see how it's working? It does know that it's going left and right. Right? So it knows left and right. But it doesn't know to go up and down. Like, it's just averaging it out. I don't want to do an average. You're not behind. Don't worry, you're not behind. You're doing good. You've got... What was it? Was it Bloomberg? Bloomberg, who's a billionaire, got started at 40. Got started at 40. Isn't that crazy? And was able to become a billionaire after getting started at 40. So you've got plenty of time. Don't worry about being worried about not having enough time there. You're good. You're good to go. Do you think pocket dimensions could be made with portals? I think so. I think you could create... Isn't that what we are? Is our universe not a pocket dimension? I think it is. I think we're in a big bubble of existence where there are multiple universes, and we are in a bubble of our very own. It only takes 2 portals to make a new world. It might only take 1 portal, right? A pocket dimension. You can make a traversable fast track, though. Try L1 loss, maybe even lower power than 1. Okay, we'll try that. We'll try L1 loss. Although we are doing MSE, mean squared error, so we want to do mean absolute error. Let's do L1 loss, right? We pulled that up here, right? Was this, no, was it earlier? Where is our losses at? All right, so L1 loss. All right, we'll try this. We'll try it. We'll see where it goes. MSE, where's our MSE? Okay. There we go. There we go. All right, let's look at it. Let's go. Ooh, it's running around. Look at that. Ooh, it's running around, just trying to figure it out. It's trying to figure it out. It is centering out. I think we need L1 loss looks okay. As you can see there, yep. I should make that it's doing okay. It's doing okay. Is it doing better? It is. L1 loss is doing better. Look at that. That is pretty neat. Okay, so yeah, it's getting there. What? Oh, yeah, it's predicting it. It is predicting. It's still going in the center, though. It's still in the center. It's still doing center stuff. Like the idea you don't want to over penalize big mistakes, so the model makes more guesses. Hey, Quantify Quantum, welcome. Merry Christmas. I'm glad you're here. Merry Christmas. What are we up to? Check this out. So we've got your model. We've got your Hey, look at all the clicks. See all the clicks that are happening? We stored and saved the clicks, and now the AI is trying to predict where the user is going to click next. Isn't that neat? Isn't that neat? Check it out, Quantify Quantum. You started this. You started it. We made it possible. We're making it look. We're making it work. We're trying to see. We're trying to see. So right now, obviously, there are multiple outcomes here. You can create 2 different possible applications for models. One of the applications is to predict where the user is going to click next. The other is this a user that is a human or a user that is an AI or a machine? That is a different kind of model or a different kind of output. All right. I need to, what I want to do is change the features. Replace L1 with YX to the power of 0.3. Do we have, can we make a custom loss function? Let's try that. I'll see if we can do that. All right, so Pytorch custom loss function. How do we do that? Because I want an unbroken graph. This is one of the main requirements for this project is that we're using all the Pytorch. We're using all Pytorch direct functions. Custom loss. Okay. Targets loss. Okay. Loss.backwards. Torch.mean. Okay, excellent. However, wait one moment. Let me see here. Optimizer.step optimizer. Parameters. Okay. I'm trying to understand how the Pytorch knows that the optimizer is going to be capturing the gradients. There must be some sort of state. MM, thank you for subscriptions. Thank you for subscribing. Welcome on in. Merry Christmas. We're doing some AI right now. Without using the help of a code generator or no Copilot. We are using search. We are reading the docs. So, but we're manually doing this all ourselves. You should pick up it fine, like you're really paranoid using Norm. It'll work. I know it'll work. I want to do it the Pytorch way because I've always been doing it the Steven way or my own custom way. Steven, have you heard about info hazard or cogni hazard? Nope, I have not. I don't know what that is. It keeps hidden states around after running because of dynamic graph. If you do a trace, what it does is it wants to see the graph it made. Oh, there's a trace? Pytorch trace. Look at that. Trace. What does it print? Oh. I want to see what that looks like. I want to see what trace looks like. Every click I want to run trace. Let's see here. Train. Okay. Predictor.trace. Oh, do we have to run features through it like that? Okay. I want to see what that looks like. Trace. Object has no attribute trace. Did you mean train? Torch.trace. Oh, okay. Got it. Let's see. There we go. See what that looks like. Okay, bye everyone. Oh, that also didn't work. Bye everyone, gotta go to sleep. All right, cool. Rashab, thank you for hanging out. Steven blink thrice if you are under NDAs. Well, I'm under mini NDAs. So yes, mini NDAs. That's why I have to be careful about what I say. It's a separate package, I think. There's something like freeze. Got it. Okay, normally Pytorch purposely does not make a static graph. Got it. Okay. I will delete that for now. Although I really wanted to see that. I think that would be really neat. Oh, that would be so neat. Oh, come on, please work. No. All right. Fine. Let's double check. Did I miss anything? Torch.trace. Returns to some of the elements. Oh. Well, that's not what I want. Let's see. Pytorch. Visualize graph. Visualize the graph. To visualize Pytorch computation graph, you can use built-in tools like TensorBoard. Visualize computation graph. Okay, we have to do extra. All right, I'll do that later. I just thought it would be neat. I think it would be neat. Yeah, showing the actual model graph is a TensorFlow thing. Got it. Yeah, that's what I want to see with Pytorch as well. I think that'd be really neat. Okay, so output. We don't use any output here. Output prediction. Okay, that's fine. Whatever. Okay, let's get rid of that. I also, or let me add this. We need to do here. I'm gonna add to do. Add more XY chords. All right. Oh, we are Bloodfire. How's it going? We are so back. Nice. Merry Christmas. Good to see you. The entire idea is go super dynamic, so it's much harder to mess up the gradients. Got it. Yeah. See, that's got it. Yeah. So I want to be careful about the breaking the graph is basically impossible. Even if I do the math myself, I would be able. So the thing is, in order to calculate the loss with Pytorch, I still have to use a tensor in Torch. So we're making our way. Okay, so wait. Where was your? 1 second. I want to go back up. So you said replace L1 with this right here. I'm going to do this. All right. So L1. It's here with this. Okay. So we need to replace that. We'll try that. We'll try that. So your target, right? Target and loss or output or prediction. Prediction minus target. Okay. So we need that instead of L1. So self.loss equals, and we need to define it somewhere. Def loss self. Did we already do this? I know we got started on it. Okay, we didn't. Self loss. Expect it. Let me double check. Output and labels. Okay. Yeah, we need output and labels. Okay. Have you ever tried HMD global devices? I do not know what that is. I'm quantified quantum. Tell us what that is. What is that? I don't even know what that is. Return output minus labels. So that should do the trick right there. All right, Neva. All right, Neva, we've got your custom loss function. I do believe that should be it. Self.loss. All right, that should work right there. Since it's saving the tensors. Got a sub, bro. Nice code to Compass. Thank you. Thank you for your subscription. This is a channel where we code. Wait, Bloodfire, tell us. Tell us what? Right, tell us, right. Right, Quantified Quantum. What is HMD Global Devices? What is that? Is that like a microprocessor device that's handheld that you run around and you scan things with? You scan for things like other kinds of signals, other types of RF radio frequencies. Basically a smartphone manufacturer, EU based. Oh, is it? Okay, so it's a smartphone and they are based in the EU. Good to know. Good to know. Okay. Huge respect for people who still write code themselves, right? Thank you. Yeah, that's what we're doing. We're writing code ourselves. Important because we want to not atrophy. It is very easy to quickly. I've done this. I've been using all the AIs, Claude Code, Codex, Gemini, to write my code for me. It's a lot of fun. It's still a lot of fun. It took a while to figure out. Now I'm really good at it, and I became dependent on it. So instead, let's stream code live, all from scratch, by hand, writing code. There you go. Love your Python ASM streams, bro. Thank you, Bloodfire. Thank you. Yeah, that's the plan. So we'll be doing more AI. We're focusing a lot on AI. We'll be doing some more assembly. We'll learn some more assembly. We haven't finished. Yeah, I know, right? Yeah, that's it. We're doing it. That's exactly what's happening. Okay. So I think that should work fine, maybe, because we are doing the math calculations directly on the tensors. So that should be an unbroken graph. So let's try it. It had an issue. Bitwise. Oh, right. Because we have to do that. In Python, it likes that syntax. All right, now we got a runtime error. Oh. Uh-oh. Okay. So this is what I thought was going to happen. Gradient can be implicitly created only for scalar outputs. So this is what I thought was going to happen. Where was this at here? Where was that at? Is it around here somewhere? Where do we have that at? Custom. I want a custom. All right, Pytorch custom loss function. Let's bring this back. Yeah, this is exactly it. Torch.mean? Oh. Do we have to do this? Oh, we have to run specific torch functions on it, or else backward won't work. Okay. Try .mean. Okay, we'll try .mean. We'll try the .mean. Okay, so we'll do this. Torch.mean. Okay, that should work. Well, it didn't work. Syntax error. Okay, got it. All right, so that's another error. That's a completely different error. Okay, so we can do that. That was at line 171. 171. Okay, here we go. Oh. Chord. Why was that? Loss, not a number. Constant, not a number. Oh, okay. So our output is failing. Okay. Actual and predicted. Oh, thank you, Neva. Thank you, Neva. All right, I'll try it. So we got our loss failed. Let's see. Loss. Okay. So that won't work, but we want to do this. Okay. So labels actual. Okay, so we go like that. Times 2. .mean. Okay, we'll try that. We'll try that syntax. Here we go. Like that. Okay. It just has to be a scalar. You can't gradient a full matrix. Makes no sense. Okay, got it. Yeah, the output needs to be a single value, unless, or a single dimensional array, right? Okay, we're trying that. We'll see if that works. Hey, there we go. All right. Hey, Neva, look, it's working. It's working in a way, although it is going to the very center of the screen, right? It's going super center. Like it's basically finding the average. It's finding the average. Also, the 2 later, there is a .3 something. All right, we'll try the .3. We'll try it really quick. Although, see, it's getting perfect center. As you can see, it's finding the center, which is a problem. Let's see here. Let's do 3. We'll try different. How'd you come up? Oh, okay, got it. Yeah. So it won't. It has to be 2. It has to be 2 like that. Which makes me wonder: can we run this type of syntax but with 2? Which will make it a. Okay. If you went back to mean squared error, if you recall, it doesn't work well with MSE because it gets paranoid. It's like, what do you mean it gets paranoid? I love that. I love that so much. Hey, Savon, how's it going? Ho, ho, ho. Merry Christmas. Merry Christmas, Savon. Good to see you. Welcome on in. Yeah, I believe in you. Nice. How'd you come up with this idea, though? Quantified Quantum did. Quantified Quantum came up. And then chat, come from Callister and some other folks, they came in and were like, hey, what if we added this feature? What if we added this? What if we did it like this? You know, what if we did this? And then we just kept piling on a whole bunch of different ideas. And that's how it worked. Merry Christmas. Good to see you. Well, nice. That was fantastic. I see it plays with itself yet. Having to not have to click anymore yet. That was one of the ideas today. They're like, hey, why don't you just have it click for you? I'm like, oh, that sounds so much better. Let's have it click for us. It's fantastic. That's why I said try lower power. Yeah, we got to try lower power. The heat map is what I'm waiting for. We could do the heat map. We could. So that's like another thing that we want to do. We could have, so like this little golden dot will predict all the previous predictions of the AI. So that's the heat map. So we could do that as well. We can do that. We can absolutely do that. So we're using Pygame. Can we, in Pygame, create a alpha? Can we do alpha transparency? Do a .pow. Okay, I'll try that. Instead of a 2, okay, let's try this. Okay, so instead of 2, like this, do a .pow. You said .pow 0.3. Okay, try that. See if that works. Nope, it's got a nan. It's the same problem. Merry Christmas, the tech man. Merry Christmas. Thank you for saying. Happy to have you here. How is the autoplay implemented in brief? So what we did was, it's actually really easy. It's just JSON. So here, what we did was we track all the clicks in the previous clicks array. So we track all the previous clicks. Then when, right here, so see, this is where we append it. Track all the previous clicks. Easy. Then we save all the previous clicks. Right? We save, that's the load, but you get the idea. Before we close, right? Before close, right here, before close, we save the previous clicks to a JSON file. 5 clicks. So you can see here, we've got a click with a bunch of JSON in it right here at the screen. A bunch of clicks. Do abs.pow. Okay. I will. Can't take the root of a negative. Why JSON though? It doesn't have to be. It's just easy. It's just easy. It's easy serialization. Why not take a CSV or something? We could do that too. We absolutely could. There's no reason. I just chose an easy option because it's really easy. Because the CSV requires extra code. Look, this is only 2 lines of code here. Easy, right? We're going for easy. Super easy. And then we load the previous points right here. And so every time we add clicks, basically what we're doing is we're getting more data. And then we save the file on close and we reopen it and we load the data and we add more clicks. And so it's an ever-growing list of clicks. So it's more and more data. So that's what we're doing. And that's how that works. Really easy. A super simple, easy approach. Okay. 1 second here. Also, JSON is more obvious to edit. Yeah, it's true. It is easy. Like if I needed to go in and edit it and make some adjustments or things like that, we could. It's a little easier to manipulate. We can manipulate easily. Same could be said with CSV, of course. Same could be said with CSV. Though JSON programmatically is easier to deal with. All right. So, all right, let's do it. All right. So abs.pow. Okay. So torch dot. torch.abs.pow or torch.abs.pow mean. All right, let's try that. Run the Python main. Here we go. All right. Oh, it's working now. It's working now. Neville, look, it is working. All right, you did it. All right. It's, what are we doing? But we generate the clicks randomly at the bootstrap, or we record manual. We're recording. It's recorded. It's pre-recorded, live, real. These are all my clicks. What you're seeing are real human clicks. Whoa, look at that. Okay. It's not getting to the center anymore. It's picking. It's being weird though. It is. What is this? Okay. It's doing some weird stuff. It's definitely different now. Look at that. Look how far it's going. It is. It's different. Like instead of going to the very center, now it's going to center top, which is different. It's definitely different. Yeah. It's neat. It's neat. I like it. All right. All right. So we do got to get going here in a little bit. Maybe do .5. Okay. We'll do .5. We'll try .5. Like play with the value. Okay. .3. Go to .5. All right. Here's .5. Oh, it's running around. It's running around. It's trying to learn. It's trying to learn. See, I think one of the problems is the learning rate decay is weird. The learning rate decay is weird. Let's see here. So it's predicting now. It is. It's doing the best. I mean, it's finding the average for the most part. It's doing okay. It's doing weird stuff though. It's doing like we need to optimize it. We need to train it. We need to do some different things. I want to add more inputs and see what it does. So I want to add 4. Right now it's only doing 2 inputs of the feature, right? X, Y, X, Y, X1, Y1, X2, Y2. Oh yeah, maybe remove decay. I would love to remove decay. Is there a way? Okay, let's actually do that. So Pytorch, one second. Pytorch remove decay. Let's remove decay on training. Weight decay is 0. Okay. Let's try this. Let's try that. Let's see if we can make that work. We could also set, what is this? No decay params. What is that? No decay params that append. Oh, you can do it for bias and for the parameters. Neat. Decay. Okay. For more granular control, I just want, let's do it like this. Okay. Actually, some weight decay may do it well. Green bean, how's it going? What are we doing? Green bean. We have got ourselves here a AI that is learning to track user clicks. As you can see, all the green dots are live. My clicks, I clicked previously, so it's my live. Live on stream. We really clicked live on stream, and the gold circle is the AI. That's how you remove learning rate decay. Yes, that's what we want to do. So we're learning from AI to make AI. You got it. I mean, in a way, because we were Googling for some help, right? So we're reading. Essentially, I call it reading the docs. Instead of having to parse through like Stack Overflow or searching through the docs directly, we are getting some Gemini help directly, which I think is fine. I think we're doing okay there. Okay. Gemini. Yep, Geminal. We got the Geminals here. We got the Geminals happening. The Geminals. All right, what was he doing? Optimizer decay. Okay. Optimizer is where you at here. Self dots. Okay. Let's try changing that to see if that does anything. Okay. Here we go. All right. Strong learning rate consistently. It seems to have had no effect. I'm not seeing any change. It looks about the same. It did give you the wrong answer here because you want to remove LR decay, not weight. Oh, okay. So see, like I can tell, like nothing changed. It didn't change anything at all. Although the loss is dropping, which is pretty good. The loss is pretty low, which is great. It's just not exactly what I want. It is interesting. That is pretty interesting. Okay. To my understanding, the AI is learning to click. Yeah, green bean. Yeah, it's learning to predict where the user will click next. So essentially, it kind of is learning to click. You got it. You exactly got it. So if we took a click tracker on a real application of some sort, like a different application, we track the click positions, then yes, we'd be able to train the AI to click. That's what we're doing. Let's see here. Okay. So, it's fine. Why not have better docs tailored up to your questions? It's not cheating. It's essentially what it is. Yeah, that's exactly. Exactly, right? Savan, exactly. It's basically tailored docs. Weight decay can help with it. Stagnant as well, just adding a penalty for choosing the same click twice. Got it. What if we gave it a really big decay or a negative decay? I'm actually kind of curious to see what that does. Let's see if that does anything at all. That seems to have made it very centered. It like made it very centered. Like that's basically the center of the screen. Okay. Okay. What if we did -10? I don't know. We're messing around with it. We're messing around. Oh, whoa, that did something. That definitely did something. It's doing like the opposite now. Okay. That's too big. What if we did -1? We could make it very low. Ah, yeah. All right, that's too much. All right, so a negative number seems like it's a problem. Weight decay can help with it being stagnant as well. Just adding penalty for choosing. Okay, and the decay is too big. It can't. Change it. Change now. All weights are 0. Ah, yeah. Okay, that's why it went to the top corner. Do -5. All right, green bean. We'll do -5. We'll see what that does. Negative decay would be a bug. It is. It is a bug. It definitely is a bug. Because it's causing a problem. So here's -5, and it should crash. I would expect it to crash again. Yeah, because you can see it's right here in the bottom corner. It's right there in the bottom corner. We are running very late. We need to do start time to 5. Okay. I do got to get going here pretty soon. Sounds good. Okay, yeah, see it crashed. See it crashed, you guys. It crashed. Negative. So let's break the model for fun. Okay. Any negative decay is always a bug in all cases. Yeah, it sure did. It sure did. So let's do 0.0001. Let's go like a very small number. Let's see what that looks like. See if it does anything. Anything above 1 is good. Okay. Oh, look at that. All right, for a very small decay, it seems to have gotten off to a start. Interesting. Very interesting. Okay. It's doing something different now. It's being very different. Yeah, all right. Looks good. All right, so there's a couple... what are we doing here? Hey, Praveen, how's it going, Praveen? Merry Christmas. We're tracking... We're having the AI learn to predict where the user's clicking next. We've got all the clicks. As you can see, all the green dots, these are all me clicking. These are all me manual clicking. Manual clicking. And then it records, and every time I click more onto the screen... it saves those recordings, and it replays every time we relaunch. Anything less is basically nonsense. Yeah, exactly. Less than 1, but positive is what you want. Okay. Yeah, so less than 1, but positive. Got it. Okay. Good to know. Good to know. Merry Christmas. Yeah, Merry Christmas. All right, so let's run that again just to see what that looked like, because it's kind of neat. It's kind of neat. It kind of looks like Christmas lights, right? There's some magic in the air. All right, some little bit of magic. All right, the AI is kind of having a problem with that decay. Let's bring the decay back. Let's do a bigger, let's do like 0.1. Let's do 10%. All right, it's happier with that. It's much happier with that. See, it's running around. It's trying. It's trying. The only thing is, it's not exactly learning. It's just finding the average still. So we still need to mess with it more. Can you make an aimbot using this? Technically, yes. You would want, the TechMan, you want to do it a little differently than what we're doing. So you would want to probably use a CNN, convolutional neural network, computer vision to track where a target will be. It needs to recognize what a target looks like. And then it will allow your cursor to be moved in a direction to add sort of like a velocity to update your mouse cursor position to target whatever is on the screen at that time. So say if the screen had a target, like a target was right here, the player target was here, but your cursor was over here, the AI would need to know to start moving your mouse in that direction towards the target. So it would have to identify where the target was on the screen, and then you'd be able to like modify it. Maybe change the model to be a heat map. Then we roll from it randomly. Then the loss is relative to the roll. That sounds kind of cool. And let's say we reward high standard deviation. Reward the high standard deviation. Neva, that sounds great. I like that idea. Oh, cool, man. It was the status of the Pi game. Oh, it looks really good. It looks really good. I'll show you. Unity. So we do got to get going. Neva, I like your ideas. We need to give it more input data, I think, right? More input data. So here, check this out. So here is our game. We've made progress on it. It looks different now. It looks very different. Are you ready? Here's the game. Here we go. All right. So we are Barry, and then we added a slow AI button and an invincibility button. And then if you get close, you get extra points. This is also with Python. This is also with AI. Hey, Kyle, look at, hey, how's it going? Welcome on in. Merry Christmas. Yo, we're wrapping up here. We have to get going here. I have a Christmas to go to. I do have a family Christmas. Oh, this looks so much different. It is, right? It is different. Yeah. We've added some extra things. We made it a little bit prettier. If you get close, you get extra points, right? So you want to stay close, but not get too close that you're going to die, or that humanity will lose. So, yeah. So we're doing good. Oh, see, no, humanity lost. Wow, what game is that? So, Savon, this is a game where it's AI that learns to chase the players, the cat and mouse type game, and it's running in Unity. We did it in Pygame originally, and we added a few extra bonuses to it. So we added a slow AI button and a invincibility button. Finally, Xmas, right? Evening sounds nice. Yeah, isn't it? What's that hub UI? Oh, that's just Unity. Yeah, it's so pretty, isn't it? It's a lot better now. It's a lot better. It's Kyle though. You did do a repurpose of the game that we did originally, and it had a lot better graphics. We just have circles still. We're just in the circle zone. You like it? The trails are awesome. It's kind of neat, yeah, because it's like when you move, it's like you're moving a little bit. And then we've got little particle effects, and if you get close, and then explosion effects, and the screen shakes a lot. And Skynet 1, you guys. Oh, hey, look who's on the screen now. It says Unique X. I wonder who that is. Kyle. Goaty, right? Isn't it neat? I think it's pretty neat. Kyle, it's you. You're the player name. now. All right. I like this better. It's kind of neat. I like it. So the AI is it is learning. It's learning strategy, which is different. Oh, darn, it got me. Anyway, all right. So Neva, I liked your ideas. I want to do those as to-do items. Don't kill you. I know. Wait, you're alive again. You're alive again somehow. I don't know. All right, we'll try to keep Kyle alive for as long as possible. We'll see if we can keep Kyle alive. Try to get some points here. And see, I like it because it's the mouse cursor. I like the mouse cursor. It's a lot more fun. Hey, Baggish, Merry Christmas, brother. Merry Christmas. Thank you for stopping in and saying hello. You want to do a shader for the border of the AI? That would be so good. That would be great. That would be phenomenal. I do have a little bit of a drop shadow effect. Uh-oh. It's starting to learn now. It's starting to learn really well. How are the names coming in the game? We added when we started the game. Oh, Kyle. They're coming for you. So the names, when we very first started the game, we added an array, and the name is randomly selected. This is tough. Oh. It's coming for you, Kyle. It's coming for you, Kyle. Oh, you got it. Kyle, it got you. I posted an advanced prompting guide in Discord. Nice. It's very long, but people might find it useful. Thank you for doing that. Yeah, it can be fun, like hours making it. The shader, isn't it? Oh, so good. This game is tough. It is very tough. It's a tough game. All right, you guys, that was it. I do got to get going. Merry Christmas, everyone. We'll be back tomorrow, even on Christmas Day for me, and Christmas Day we'll be back tomorrow, the day after Christmas for some. We'll continue getting our click tracking AI to see if we can optimize it to do it a little bit better. So that'll be the plan. That'll be the plan for tomorrow. Thank you, Neva. Thank you for all your help, Neva. You've helped a lot. We're learning together. We figured things out. Night. Enjoy Christmas. Enjoy Christmas, everyone. We're headed out now. It was good to have you here. That was a lot of fun. Thank you, everyone. Have a great Christmas yourself. We'll be back tomorrow. There we go. All right, bye, everyone. See you tomorrow. Thank you for streaming. Thank you for joining the stream. Merry Christmas, Kyle.